Tonight, we are moving toward one of the strangest boundaries in physics, the speed of light. It sounds like a simple limit. Light crosses a vacuum at about 300,000 kilometers per second. Nothing with mass, we are told, can be accelerated beyond it. From that statement, the imagination quietly builds a wall. On one side is the familiar universe, where planets orbit, spacecraft travel, and messages move through darkness. On the other side, perhaps, waits a hidden realm where distance collapses and the ordinary order of events no longer applies. But that picture is misleading. The speed of light is not a wall standing somewhere in space. It is not a surface a powerful engine might eventually strike. It is not even best understood as a special property belonging only to light. It is woven into the relationship between distance, duration, motion, and cause. When physics says that an ordinary object cannot simply accelerate past light, it is not describing a temporary failure of engineering. It is describing the structure of spacetime itself. That changes the question. What really happens beyond the speed of light? Do we mean what happens when a spacecraft tries to cross the limit? Do we mean regions too distant for light to reach? Do we mean effects that appear to move faster than light without carrying matter or information? Or do we mean the expansion of the universe, where the distance between remote galaxies can increase faster than a beam of light could cross it? These are different physical situations. They only sound alike because ordinary language places them beneath the same dramatic phrase. Nature gives us several effects that look superluminal. A spot of light may sweep across a distant surface faster than light. A charged particle may outrun light as it propagates through water and leave a blue glow behind it. A remote galaxy may recede from us faster than light because the space between us is expanding. Entangled quantum particles may display correlations that seem to ignore distance. Mathematical solutions to Einstein's equations can describe shortened paths through curved spacetime. Yet none of these has given us an ordinary traveler or controllable message that begins below the vacuum speed of light, crosses the boundary, and continues beyond it. That missing crossing is the heart of tonight's journey. By the end of tonight, you're going to understand why the speed of light is not merely the fastest speed in the universe, why several genuine faster-than-light effects do not violate relativity, why controllable superluminal information would disturb the order of cause and effect, and why beyond light is less a hidden destination than a different relationship between events. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Imagine a spacecraft moving through empty interstellar space. Its engines fire gently. The crew feels a steady pressure beneath their feet. Loose objects settle toward the rear of the cabin, as though a weak gravity were pulling them down. Outside, the stars ahead become brighter and bluer, while the stars behind shift toward red. From Earth, the craft moves faster and faster. It reaches half the speed of light, then 9/10, then still closer. Its engines continue operating. The crew does not feel an invisible barrier pressing against the hull. Nothing in front of them becomes solid. There is no luminous gate waiting in the darkness. Yet the relationship between the spacecraft and Earth begins to change. The clocks aboard the ship no longer advance at the same rate as clocks at home. The distance to the destination is not measured the same way by the crew and by observers on Earth. Each additional increase in speed requires more energy than ordinary intuition predicts. The spacecraft can approach the light-speed boundary with extraordinary closeness. It never completes the crossing. This is where everyday experience becomes unreliable. At familiar speeds, velocities seem to add directly. If a train moves forward and someone walks toward its front, an observer beside the track measures the walking speed combined with the train's speed. It is natural to assume that a spacecraft should work the same way. Add more thrust, gain more speed, and eventually pass any chosen value. Relativity says that this simple addition rule is only an approximation. It works beautifully for cars, aircraft, and planets because their speeds are tiny compared with the speed of light. Near light speed, space and time no longer behave like separate, universal measurements shared by everyone. They adjust together. Every freely moving observer measures light in a vacuum traveling at the same speed. An observer on Earth measures it that way. The spacecraft crew measures it that way. Someone moving rapidly toward the beam or away from it also obtains the same value. They may disagree about elapsed time. They may disagree about distance. They may even disagree about whether two distant events occurred simultaneously. They do not disagree about the vacuum speed of light. This is not because instruments become inaccurate at high speed. It is because measurements of space and time are linked by the geometry of space-time. So the first answer to the title is unexpectedly quiet. For ordinary matter, there is no known physical experience of crossing beyond the speed of light. The traveller never reaches the boundary and discovers what lies on the other side. The path toward it becomes increasingly demanding, and the crossing never appears within the allowed motion of a massive object. But the word beyond still has meaning. Physics describes pairs of events separated by so much space and so little time that even light could not travel from one to the other. These events are spacelike separated. They do not exist in another dimension. They are simply too far apart to be connected by any known signal during the available interval. There are events beyond one another's reach. That is the deeper boundary we will follow. The universe is not divided into a slow interior and a fast exterior. From every event, there is a region that can influence it, a region it can influence, and a wider region beyond immediate causal contact. Light marks the edge. A massive object remains inside that edge. Light itself follows it. A genuine faster-than-light signal would have to connect events outside it. Once that happens, the problem is no longer only speed. It becomes a problem of order. In one frame of reference, a superluminal signal may appear to travel from event A to event B. In another moving frame, the assigned timing can reverse so that B occurs before A. That cannot happen to ordinary cause and effect. Observers may disagree about how long a journey lasted, but they agree that departure came before arrival. Beyond the light-speed structure, that agreement is no longer guaranteed. We will approach this carefully. Nothing in relativity says that time becomes fantasy, or that every unusual wave effect creates a paradox. The physical details matter. Whether information is transmitted matters. Whether the effect is local matters. Whether a measured speed belongs to an object, a pattern, or a changing distance matters. Tonight, we will keep those possibilities separate. The broad answer is already taking shape. Beyond the speed of light is not a country waiting to be entered by a sufficiently powerful machine. In known physics, it is a category of separation, a family of appearances, and a frontier where our familiar confidence in the order of events becomes fragile. The boundary is real. It is simply not where common sense first places it. The boundary becomes clearer once we stop treating light as though it were merely a very fast object. A stone has a speed relative to the ground. A spacecraft has a speed relative to Earth, the Sun, or another spacecraft. Sound travels through a material such as air or water, and its speed depends on the properties of that material. For a long time, it seemed reasonable to assume that light must behave in the same way. Waves on water require water. Sound waves require matter. Perhaps light waves also moved through an invisible substance filling all of space. This proposed medium became known as the luminiferous ether. If Earth moved through the ether while orbiting the Sun, a kind of ether wind should have existed. A beam of light travelling with that wind should have behaved slightly differently from one travelling across or against it. In the late 19th century, Albert Michelson and Edward Morley built an experiment designed to detect that difference. Their interferometer divided light into two perpendicular paths, reflected both beams, and brought them together again. If Earth were moving through a stationary ether, the beams should have required slightly different travel times. Their recombination should have produced a changing interference pattern as the apparatus turned and as Earth changed direction during its orbit. the expected shift did not appear. The result did not instantly create special relativity, and it was not the only clue that older ideas were failing, but it became one of the clearest signs that light did not behave like an ordinary wave moving through a fixed material background. The deeper difficulty was not simply the absence of an ether. The old ideas of space, time, and motion no longer fitted together. Einstein's special theory of relativity began from two principles. The laws of physics should take the same form for all observers moving steadily relative to one another, and every such observer should measure light in a vacuum traveling at the same speed. These statements sound modest. Their consequences change almost everything. Imagine two spacecraft moving apart in empty space. One sends a beam toward the other. From the first craft, the beam departs at the speed of light. Everyday intuition suggests that the second spacecraft, moving away, should measure the beam approaching more slowly. It does not. The second crew still measures light traveling at Now let that spacecraft turn and move rapidly toward the source. Simple addition suggests that the approaching beam should be measured as faster than light. Again, it is not. The crew obtains the same value. Light does not detect an observer and adjust its speed, nor is one spacecraft secretly at rest in a preferred universe. There is no experimentally confirmed state of absolute steady motion. Instead, the observers disagree about the measurements used to calculate speed. Speed is distance divided by time. If moving observers must obtain the same value for light, they cannot all share one universal measure of distance and one universal clock. That is the quiet revolution. Space and time are not independent stages on which motion takes place. They form a connected structure, and observers moving relative to one another divide that structure differently. A light clock makes the idea easier to picture. Imagine two mirrors facing one another inside a spacecraft. A pulse of light travels between them, and each round trip marks one tick. To the crew travelling with the clock, the pulse moves straight upward and downward. The mechanism behaves normally. An observer watching the spacecraft pass sees a different path. While the pulse crosses between the mirrors, the spacecraft moves sideways. The light therefore follows a longer diagonal route from the outside observer's perspective. But the outside observer must still measure the light travelling at the same speed. A longer route at the same speed requires more time. The moving light clock appears to tick more slowly. This is time dilation. The clock is not damaged, and the effect is not an optical illusion. Every physical process aboard the spacecraft follows the same timing when described from the outside frame. Electronic pulses, chemical reactions, heartbeats, and aging. The crew does not feel slowed. Their own clocks behave normally. Their thoughts, meals, and conversations unfold at the usual pace. The difference becomes evident only when observers who followed different paths compare their accumulated time. Distance changes as well. A rapidly moving object is measured as shorter along the direction of its motion. This length contraction is not mechanical crushing. It follows from how moving observers define the positions of an object's front and rear at the same time. And simultaneity itself becomes relative. Two events that are simultaneous for one observer may occur at different times for another observer moving relative to the first. This remains true even after ordinary signal delays have been corrected. To preserve the invariant speed of light, nature does not alter only clocks. Measurements of time, distance, and simultaneity transform together. The mathematical rule connecting these measurements is the Lorentz transformation. At everyday speeds, it reduces almost perfectly to the older rules associated with Galileo. That is why ordinary intuition developed without noticing relativity. Near light speed, the difference becomes unavoidable. The quantity c therefore does more than describe photons. It acts as a conversion between space and time. A second can be associated with the distance light travels during that second. A distance can be associated with the time light requires to cross it. In spacetime geometry, c determines which events can be causally connected. This is why the limit applies even when visible light is absent. Changes in electromagnetic fields do not transmit information faster than gravitational disturbances also obey the same causal structure. When the gravitational wave event GW170817 was observed in 2017, gravitational waves and gamma rays from the same distant neutron star merger reached Earth with only a small difference after traveling for roughly 130 million years. The measurement placed an extraordinarily tight constraint on any difference between their propagation speeds. The causal limit belongs to spacetime, not to brightness. This also explains why a spacecraft can never chase a light pulse until it hangs motionless beside the window. No matter how rapidly the craft moves, the crew still measures the beam passing at sea. What changes is the light's frequency, the timing of distant events, and the relationship between the crew's coordinates and Earth's. The beam never surrenders its speed. It may seem as though the universe performs an elaborate adjustment to protect one special number. A better interpretation is that the number reveals a geometry that was present all along. Each observer carries a valid way of assigning times and positions to events. They may disagree about the spatial and temporal parts of a separation, but they agree on a deeper quantity called the space-time interval. Light occupies the special case in which that interval is zero. Its paths form the dividing lines of causal structure. Different observers draw their coordinate grids differently, yet those light paths remain the shared boundary. The invariant speed of light is therefore not an arbitrary traffic law. It is the visible edge of a deeper agreement. Observers may carry different clocks, they may measure different lengths and assign different times to distant events, but when they trace the paths that physical influence can follow, the boundary remains the same. That is why ordinary velocity addition fails near sea. Relativistic velocity addition ensures that combining any two sublight motions still produces a result below light speed. The value may approach the boundary with extraordinary closeness. It does not pass through, and once the limit is recognized as part of spacetime rather than a property of a beam, a practical question appears. What happens when a massive traveler keeps accelerating toward it? A massive spacecraft can continue accelerating for a long time without ever feeling light speed as a physical barrier. Inside the cabin, the engines push the crew gently into their seats. A clock above the instrument panel ticks normally. A cup placed on a table behaves as expected. If the acceleration remains similar to Earth's gravity, the travelers can stand, sleep, and work while the ship gains speed relative to the planet they left behind. They do not see a speedometer approaching a universal red line. Their speed exists only relative to something else. Relative to a companion craft moving beside them, they may be nearly at rest. Relative to Earth, they may be traveling at 9/10 of the speed of light. Relative to another distant object, the value may be different. There is no single cosmic speedometer suspended in space. Yet every inertial observer agrees that the massive spacecraft remains below sea. To understand why, separate what the travelers feel from what Earth measures. Suppose the spacecraft maintains a steady acceleration. From the crew's local perspective, the engines continue changing their motion. They feel no weakening of the thrust merely because Earth says they are moving quickly. But observers on Earth do not add the ship's successive velocity changes using the ordinary rule of daily life. Near light speed, each additional gain measured from Earth becomes smaller than classical mechanics would predict. The spacecraft may pass 90% of C, then 99%, then 99.9%. More nines can be added. The gap becomes extremely small. It does not become zero. The engines still transfer energy to the spacecraft, but increasingly, that energy appears as greater relativistic momentum and a stronger difference between the ship's time and Earth's time, rather than as a simple increase in speed. Older explanations often say that the spacecraft's mass increases. That language can be confusing. In modern treatments, its rest mass remains constant. A kilogram aboard the ship is still a kilogram for the crew. What grows dramatically is the total energy and momentum measured from a frame in which the ship is moving rapidly. Relativity expresses this growth through the Lorentz factor. At ordinary speeds, the factor is almost exactly 1. At 90% of light speed, it is already a little more than 2. At 99%, it is more than 7. As the speed approaches c, the factor rises without limit. This quantity appears in time dilation, length contraction, energy, and momentum. For Earth, the ship's clocks run slowly. For the crew, the distance to the destination is shortened along the direction of travel. For Earth, the ship's momentum grows much faster than its velocity. The closer the spacecraft comes to sea, the more energy is required for a smaller, measured increase in speed. Reaching exactly light speed would require unlimited energy. This is not merely an inconvenient fuel estimate. It is not comparable to needing a larger rocket or a more efficient reactor. It is a mathematical limit built into the motion of anything with non-zero rest mass. Every finite amount of energy leaves the ship below sea. Particle accelerators reveal this relationship in the laboratory. At CERN, the Large Hadron Collider accelerates protons to speeds so close to light that the difference is difficult to express naturally. The protons move at more than 99.99999% of Increasing their energy does not push them visibly beyond the limit. Instead, their momentum grows, and the energy released when they collide becomes enormous compared with the energy associated with their rest mass. The accelerator is not failing to accelerate them. It is changing the quantity that matters most near the boundary. The protons gain energy. They gain momentum. Their collisions can create new particles and expose processes invisible at lower energies. Their speed only creeps closer to c. The final part of the gap is never crossed by one last push. There is always another fraction remaining. For the travelers aboard a spacecraft, however, relativity permits something nearly as remarkable as a faster-than-light journey. Imagine a destination many light years away. According to Earth's clocks, a ship traveling below sea cannot arrive in less time than light would require to cross the distance, even before accounting for acceleration and braking. But the crew may experience far less time. As their speed rises, the distance ahead becomes contracted in their frame. Their onboard clock continues ticking normally, yet fewer of those ticks may pass before arrival. A journey lasting decades or centuries on Earth could occupy only years for the travelers. The ship would not outrun light. The crew and Earth would measure the same journey using different divisions of space and time. Picture one traveler standing beneath the cabin clock before departure. She glances at a photograph of a child remaining on Earth during the voyage. She eats, sleeps, works, and watches only a few years pass. At the destination, the clock above her still looks ordinary, but the child in the photograph may now be elderly or long gone. Relativity does not merely alter numbers on a navigation display. It separates lives. These effects make relativistic travel theoretically powerful, but the physical environment would be severe. At extreme speeds, the thin gas between stars becomes dangerous. Hydrogen atoms strike with high energy. Dust grains become impact threats. Light ahead shifts toward shorter, more energetic wavelengths. Shielding must absorb radiation and collisions while surviving its own heat. The spacecraft must also accelerate and later slow down. Carrying fuel adds mass, and accelerating that fuel requires still more energy. Navigation errors that seem tiny at departure can become enormous across interstellar distances. These challenges may stop a real vehicle long before relativity's formal boundary becomes the dominant engineering problem. But they do not create the boundary. Even in a perfectly empty universe, with flawless engines and unlimited ordinary resources, a massive spacecraft would remain below light speed. The key point can now be stated precisely. A massive object does not lose the ability to accelerate in its own local experience. It does not strike a wall. It does not freeze in place. Instead, the relationship between energy and velocity changes so strongly that no finite energy completes the crossing. Light is different. A photon does not begin at rest and accelerate until it reaches c. In a vacuum, it is created already traveling at the causal speed. There is no valid inertial frame in which a photon is stationary. Asking what a photon experiences at rest is therefore not a meaningful physical question. No observer can travel beside it at sea and construct a normal clock and ruler frame. Massive matter occupies one class of paths through spacetime. Light follows the boundary of that class. A hypothetical faster-than-light entity would occupy another class entirely. The equations do not provide an ordinary road carrying one into the next. There is no final thrust that turns a spacecraft into light. And there is no further thrust that places it beyond light. That missing road is more important than the energy cost. It means the question is not merely why our engines remain too weak. The deeper question is what kind of path a faster-than-light object would have to follow, and why that path changes more than speed alone. The difficulty becomes sharper when we ask what the crossing itself would look like. Not the approach, not the growing energy requirement. The exact transition from slightly slower than light to slightly faster. Ordinary motion encourages us to expect such a moment. A car can move from 40 kilometers per hour to 41. An aircraft can pass the speed of sound. Even when a threshold produces dramatic effects, the object follows a continuous sequence of permitted speeds. At one moment, it is below the threshold. At another, it is above. Light speed does not behave like that. A massive object may approach c indefinitely, but relativity provides no physically allowed state in which the object reaches the boundary, rests there for an instant, and then continues through it. The missing step is not hidden by inadequate technology. It is absent from the structure describing massive motion. Return to the spacecraft. Relative to Earth, its speed becomes 99% of light speed, then 99.9%, then a value with many more nines. Every finite addition of energy brings it closer. Now try to describe the next stage. At exactly c, the mathematical quantities describing the energy and momentum of a massive spacecraft would no longer remain finite. Time dilation relative to Earth would grow without limit. Length contraction along the direction of motion would approach an extreme boundary. These statements do not mean the ship physically flattens into nothing or that the crew watches their clocks stop. They mean the transformation used to describe an ordinary massive object cannot be extended into a valid rest frame at light speed. There is no frame in which the spacecraft moves at c relative to Earth while remaining stationary relative to itself in the ordinary sense. Its familiar rest frame cannot exist at that boundary. Rest mass is connected to the possibility of describing an object in a frame where its total momentum is zero. A planet has such a frame. A person has one. A spacecraft has one, regardless of how rapidly it moves relative to Earth. Light does not. No change of inertial frame can bring a photon to rest. Every valid observer still measures it moving at c. A photon is therefore not a massive particle that has simply been pushed as fast as possible. And a massive particle is not a slow photon waiting for a more powerful engine. Their allowed motions belong to different geometric classes. For a massive traveller, time passes along the path. A clock carried aboard the ship records proper time. The crew ages. Chemical reactions proceed. Electrical impulses cross the cabin. A continuous personal history connects departure, meals, sleep, and arrival. Light follows a different type of path. It is tempting to say that no time passes from the photon's perspective. But that wording invents a rest perspective that relativity does not define. The safer statement is that the proper time description belonging to a massive traveller does not apply to a light-like path in the same way. A hypothetical faster-than-light object would require another class of path again. It would connect two events separated by more space than light could cross during the assigned time. Such a path is called spacelike. We therefore have three categories. Massive matter follows time-like paths. Light in a vacuum follows light-like paths. A genuine faster-than-light influence would require a space-like path. The categories touch at a mathematical boundary, but that does not mean matter can move freely between them. For ordinary matter, the The light-like boundary lies an unlimited energy distance away, even when the remaining difference in speed becomes tiny. The crossing point is not an ordinary intermediate state. The ship cannot pause there. It cannot pass through with a final, finite burst, and it cannot emerge beyond the limit while retaining the same physical description as ordinary matter. Momentum offers another view. At low speeds, momentum is approximately mass multiplied by velocity. Double the velocity, and momentum roughly doubles. Near the relationship changes. Momentum can continue increasing dramatically while the speed changes by less and less. An engine may still increase the ship's momentum. It may increase the energy released in a collision. It may alter how strongly the craft interacts with matter. But the velocity measured from Earth remains below. This is why adding energy to already relativistic particles remains meaningful even when their speed barely changes. Energy has not stopped entering the system. It is simply no longer producing classical increments of velocity. Suppose, however, that we abandon the idea of acceleration and imagine an entity that is already moving faster than light. Mathematics allows us to examine that assumption. Physicists have traditionally used the name tachyon for a hypothetical particle that would exist only on the superluminal side. The important idea is that it would not begin below C and cross upward. It would always move faster than light. In simplified tachyon models, adding energy would slow the object towards C from above, while removing energy would make it move faster. The boundary would remain unreachable from the superluminal side, just as it is unreachable for ordinary matter from below. This produces an intriguing symmetry. Massive matter cannot be accelerated up through C. A tachyon could not be slowed down through C. Light would remain between them. But mathematical symmetry is not observational evidence. No confirmed experiment has revealed a freely traveling particle carrying matter or controllable information along a space-like path. The absence of a crossing also removes several popular images. A spacecraft would not break through light speed in a burst of white light. It would not leave ordinary spacetime behind like a swimmer breaking through the surface of water. Its clocks would not reverse because a dial passed one special number. And an expression involving imaginary mass would not describe familiar matter acquiring a ghostly new substance. Imaginary numbers are legitimate mathematical tools. They appear throughout quantum mechanics, electromagnetism, and engineering. But when a mass term becomes imaginary under a naive extension of a familiar equation, the result warns that the ordinary particle interpretation no longer applies. The mathematics has entered a different domain. It has not shown how to transform a proton, person, or spacecraft into a superluminal object. Known physics gives us no laboratory procedure for making that conversion. We can accelerate matter. We can create photons. We can transform energy into new particles when conservation laws permit. None of these processes supplies the missing bridge. The conclusion is stronger than saying that crossing light speed would be difficult. For ordinary matter, the continuous route is undefined. The traveller can keep accelerating according to instruments aboard the craft. Earth can watch the ship approach ever more closely. Both descriptions remain valid. Neither contains a final moment when time-like motion becomes light-like and then space-like. The physical story ends before the crossing. To understand what beyond means, we must stop following the spacecraft for a moment and examine the geometry of events themselves. That geometry will show that the superluminal side is not merely a region of greater speed. It is a region with a different relationship to possible influence, communication, and time. Once the imagined crossing disappears, faster-than-light motion becomes a question about which events can be connected. Relativity describes the universe not only as objects moving through space, but as events arranged within space-time. An event can be almost anything with a location and time. A lamp switching on, a detector recording a photon, a spacecraft firing its engine, or a person pressing a button. Each event occupies one point in a structure containing 3 dimensions of space and one of time. From any event, light can spread outward. After 1 second, it can reach locations about 300,000 kilometers away. After 2 seconds, it can reach twice that distance. After 1 year, it can reach a sphere 1 light-year from the starting point. If we draw only one dimension of space and place time vertically, the expanding sphere becomes the widening sides of a cone. This is the future light cone. It contains all later events that could, in principle, be influenced by the event at its tip. A radio signal transmitted now follows the cone's surface as it moves through empty space. A slower spacecraft remains inside the cone. So does any person, planet, particle, or physical disturbance moving below C. The cone widens because influence has more time to travel farther. Another cone extends into the past. The past light cone contains all earlier events that could have influenced the present one. Light from a nearby object left only a tiny fraction of a second ago. Sunlight reaching Earth began its journey about 8 minutes earlier. Light from the Andromeda galaxy travelled for roughly 2.5 million years. When we look into space, we look down our past light cone. We do not see distant objects as they exist during one universal present. We see signals that have had enough time to arrive. Together, the past and future cones organize causal possibility. Events in the past cone may have contributed to what happens here. Events in the future cone may be affected by what happens here. The surfaces are traced by light. Outside them lies another region. Imagine one detector flashing on Earth while another detector near a distant star flashes 1 second later. Light cannot cross the separation in 1 second. Neither can any ordinary particle, spacecraft, radio transmission, or known physical influence. The two events are spacelike separated. This phrase does not mean that they exist outside spacetime. It describes the balance between their spatial distance and temporal separation. There is too much space between them for the available time. According to known local physics, neither event can immediately cause the other. That is what lies outside the light cone. It is not a destination beyond a visible barrier. It is a set of events that cannot yet communicate. The word "yet" matters. As time passes, future light cones widen. Regions that cannot exchange signals now may do so later. Earth and a settlement 4 light-years away cannot conduct a conversation with immediate replies, but messages can travel between them. Each one-way transmission requires at least 4 years in the frame where that separation is measured. Their present events may be spacelike separated. Later events can become causally connected. The light cone does not permanently divide the universe into accessible and forbidden territories. It defines which connections are possible from each event. Every event has its own cones. Wherever you are, and whenever you are there, light spreads outward from that point. Earth does not occupy the center of a universal causal map. Neither does the Sun, the Milky Way, or any other object. Each event is the tip of its own local division between possible influence and immediate isolation. This is why C is more than a speed limit. It determines the slope of causality through spacetime. A massive traveler follows a time-like path inside the cone. Light follows the cone's surface. A faster-than-light signal would have to move outside it and connect space-like separated events. On a diagram, this looks easy. Draw a line tilted farther toward the spatial direction, and the signal reaches a distant location before light. Physically, however, the relationship between the endpoints has changed. Inside the cone, cause precedes effect for every inertial observer. Different observers may measure different distances and durations, but the order survives. A transmitter emits before the nearby receiver detects. A spacecraft launches before it arrives. A match is struck before the paper begins to burn. The measured intervals can vary. The sequence does not. For space-like separated events, that protection is absent. A true faster-than-light signal would therefore do more than arrive quickly. It would convert 2 events with no universal temporal order into a sender and receiver joined by a causal influence. That is why the light cone, rather than the speedometer, is the deeper structure. The distinction also explains why local motion and large-scale separation must not be confused. A distant galaxy can recede from us faster than light because the geometry between us changes. The galaxy is not locally overtaking a beam passing beside it. In its own neighborhood, the usual light cone structure remains intact. A black hole horizon offers another example. Near the horizon, space-time is curved so strongly that all future directed paths point inward. Light still travels locally at sea. It does not slow to a halt at a material surface. The horizon is a causal boundary produced by geometry. These cases show why faster than light can describe several unrelated mechanisms. A local object crossing its light cone is one claim. A changing distance across an expanding universe is another. A pattern sweeping across a surface is another. A shortcut through curved geometry is another still. Only the first would be ordinary local superluminal motion. No confirmed observation has shown matter or controllable information doing that. The light cone structure has survived exceptionally precise tests. Particle accelerators push matter close to the cone from within. Astronomical signals travel along it across enormous distances. Electromagnetic waves and gravitational waves carry changes according to the same causal order. Our technologies depend on that stability. Navigation satellites require predictable signal travel times, and relativistic clock corrections particle detectors reconstruct collisions from ordered trace. Astronomers compare arrivals from distant explosions and mergers. Across these measurements, influence remains constrained by the cone. A deeper theory may eventually reveal that spacetime emerges from something more fundamental. General relativity and quantum mechanics are not yet united in a complete description of nature. But any deeper theory must explain why ordinary causal structure works so precisely. The central image can now become simple. From one event, light spreads into the future like an expanding surface. Slower matter travels within it. Behind lies the cone of signals that could have arrived from the past. Outside lies a broad reality that cannot touch this moment. Most of the universe is outside our immediate causal reach. That does not make it unreal. It means reality is larger than what can influence us now. And if we imagine sending a message through that outer region faster than light, the next question is unavoidable. Would every observer still agree about which end of the message came first? The answer depends on the kind of separation between the events. For events connected by slower than light motion, every inertial observer agrees about their order. A spacecraft departs before it arrives. A detector receives a nearby pulse after the transmitter releases it. Observers may disagree about the duration. They do not exchange cause and effect. Spacelike separated events behave differently. Imagine two lamps placed far apart along a straight line. One is on Earth, the other is aboard a distant station. Their clocks have been synchronized in the frame where both locations are at rest. At a chosen moment, the Earth lamp flashes. A short time later, according to those clocks, the distant lamp flashes. The separation is so large that light from Earth could not have reached the station before its lamp activated. The two flashes lie outside one another's light cones. In the Earth and station frame, the sequence seems clear. Earth flashes first, the station flashes second. Now imagine an observer moving rapidly from Earth toward the station. This observer carries a different network of synchronized clocks. Relativity says those clocks do not agree with the Earth frame, about which distant events occur at the same time. This is the relativity of simultaneity. At everyday speeds, the effect is too small to notice. We move through life with the practical impression that one shared presence stretches across a room, a city, and perhaps the whole universe. Near light speed, that intuition fails. For the moving observer, the interval between the two flashes can become smaller. At a suitable relative speed, the flashes are simultaneous. At a still greater speed, their order reverses. The station flashes first. Earth flashes second. Nothing about the lamps has changed. No one has forgotten to correct for the time required for light to reach their eyes. Even after all ordinary signal delays are removed, the observers can assign opposite temporal orders. The disagreement follows from the Lorentz transformation. Observers moving relative to one another do not merely measure clocks ticking at different rates. They also divide spacetime into surfaces of constant time differently. Events placed on one observer's line of now do not necessarily occupy another observer's line of now. The faster the relative motion, the greater the difference. This does not allow observers to reverse every sequence. Consider a glass released above a floor and then shattered on impact. The release and impact occur at nearly the same place, with enough time between them for an ordinary object to connect the events. Their separation is time-like. Every observer agrees that the glass was released before it broke. Some assign a longer interval, others assign a shorter one. None sees the shards appear before the fall. Now consider a flash, followed by its arrival at a detector. These events are like separated. Every observer preserves the order of emission and detection. Only spacelike separated events permit reversal. That fact reveals something important about time. When two events cannot influence one another, nature does not require a universal answer to which one occurred first. The universe preserves the order that matters causally. It does not preserve absolute temporal order where no physical connection exists. This does not mean time becomes subjective, or that observers may choose any history they prefer. Each frame follows strict mathematical rules. Once an observer's motion is specified, the assigned coordinates are determined. Nor does anyone watch a lamp flash backward. Every local event remains ordinary. The lamp emits light. A nearby detector responds. People standing beside either lamp agree about what happens in their own location. The disagreement appears only when distant events are assigned positions in one common temporal sequence. Picture two astronomers passing one another between the lamps. One moves toward Earth, the other moves toward the station. Each uses an accurate array of clocks, synchronized according to their own motion. They can assign opposite orders to the flashes. Neither has made a mistake. Because the flashes are space-like separated, no observer-independent order exists between them. This is where faster-than-light communication creates trouble. Suppose the Earth flash is not an independent event. It marks the transmission of a superluminal message. The station flash marks its arrival. In Earth's frame, the sequence appears ordinary. Earth sends, the station receives, but because the endpoints are space-like separated, another observer can describe the reception as occurring before the transmission. This sounds like a contradiction, but a single one-way signal does not yet create a complete paradox. The two endpoint events still exist. Different frames assign them different orders according to consistent rules. The deeper problem appears when the receiver can respond. A return signal may be arranged so that, in Earth's original frame, the reply arrives before the first message was sent. Then the frame-dependent order becomes a closed causal chain capable of reaching into its own beginning. Before following that chain, pause with the central change. Classical intuition imagines the universe carrying one great clock. Every event, however distant, occupies a definite place in a universal sequence. Observers may learn about events late, but the order itself seems absolute. Special relativity removes that background clock. There is no unique universal present joining all places. Each inertial observer has a valid way of dividing space-time into space and time. These divisions agree about local events and every possible causal sequence. They disagree only across separations where no light-speed limited influence can travel. The speed of light protects this arrangement. As long as matter and information remain inside or on the light cone, causes precede effects for everyone. Time intervals can change, distances can contract, simultaneity can become relative. Causal order survives. A controllable faster-than-light signal would cross into the one region where that protection no longer applies. It would turn events that observers may order differently into a message with a definite sender and receiver. The problem is therefore not that something travels extremely quickly. The problem is that cause and effect are assigned to endpoints whose temporal order is not universal. Inside the cone, observers disagree about measurement while preserving history. Outside it, even before and after depend on motion. And once a message crosses that outer region and returns, it may arrive early enough to challenge the event that caused it to exist. A single faster-than-light signal is strange because observers can disagree about whether it was sent before or after it arrived. A return signal turns that strangeness into a potential contradiction. Consider Alice and Ben, moving rapidly relative to one another. Alice remains near Earth. Ben travels away in a spacecraft at a substantial fraction of light speed. Each carries an accurate clock. Each understands relativity. Neither has made a measurement error. With ordinary communication, there is no paradox. Alice sends Ben a beam of light. Ben receives it later and transmits a reply. The reply returns to Alice after the original message left. The observers may calculate different durations between these events, but every valid frame preserves the sequence. Alice transmits. Ben receives. Ben replies. Alice receives the reply. Light-speed limited communication cannot rearrange that chain into a contradiction. Now give both observers a hypothetical device capable of sending controllable information faster than light. We will not decide how the machine works. We will simply assume that Alice can choose a message, send it along a spacelike path, and that Ben can receive and answer it. At noon, Alice plans to activate a dangerous engine test near Earth. Before beginning, she sends Ben a question. Did the remote sensor detect an instability? From Alice's perspective, the message travels faster than light and reaches Ben soon afterward. Ben checks his instruments. The instability is present. He immediately sends back a warning. Cancel the test. Because Ben is moving relative to Alice, his definition of simultaneity differs from hers. The outward signal already connects spacelike separated events. In some frames, Ben receives it before Alice sends it. The return signal can also follow a spacelike path. With the proper relative motion and signal speeds, Ben's warning reaches Alice at 11:55. 5 minutes before she transmitted the question, Alice reads the warning and cancels the test. But now she never sends the message that caused Ben to inspect the sensor and return the warning. If Alice does not send the question, Ben does not receive it. If Ben does not receive it, he does not send the warning. If the warning is not sent, Alice receives nothing at 11:55 and has no reason to cancel the test. The chain seems to remove the event that created it. This construction is known as a tachyonic antitelephone. The name refers to hypothetical faster-than-light tachyons, but the logic does not depend on those specific particles. Any controllable method of transmitting information along suitable space-like paths could create the same difficulty, while ordinary special relativity remained valid. The device does not merely send a message quickly. It sends information into Alice's own past. The contradiction can be made even cleaner by removing human decisions. Alice programs her transmitter to send a 1 at noon unless an earlier reply tells it not to. Ben's machine automatically sends back a 0 whenever it receives a 1. The geometry is arranged so that Ben's 0 reaches Alice before noon. If the 0 arrives, Alice's machine does not send the 1. But if the 1 is not sent, Ben never receives it and never returns the 0. The contradiction is now built into automatic equipment. No one needs to change their mind. The problem emerges from 3 assumptions. First, faster-than-light signals carry controllable information. Second, the laws of physics take the same form in all inertial frames, with no preferred state of rest. Third, the signals can be exchanged between observers moving relative to one another. Together, these assumptions permit a closed causal loop. Remove one, and the paradox may disappear. Perhaps controllable faster-than-light signals do not exist. Perhaps an effect may appear superluminal but cannot be used to encode a chosen message. Perhaps a deeper theory contains a preferred reference frame that establishes one true causal order, although that would modify the symmetry underlying special relativity. Or perhaps causal loops are allowed, but must obey a consistency rule preventing contradictory events. Each possibility carries a serious cost. The simplest answer, supported by evidence, is that usable information does not travel faster than light through a local vacuum. This is why physicists distinguish a moving pattern from a signal. A bright spot can sweep across the moon faster than light if a laser on Earth changes direction rapidly. But the spot is not one object moving sideways over the lunar surface. Different photons illuminate different locations. An observer at one point cannot attach information to the spot and send it along the surface to the next point. Nothing physical makes that sideways journey. Some wave peaks and pulse shapes can also appear to advance faster than light, but an apparent peak is not automatically the first arrival of genuinely new information. The anti-telephone requires more than a measurable velocity. Alice must be able to choose what to send. Ben must be able to decode the choice. The information must be returned in a way that affects Alice's earlier action. Without control, there may be correlation. Without new information, there may be prediction or reshaping. Without a return path, there may be unusual ordering without a closed contradiction. The full causal loop requires them together. A theory could attempt to preserve faster-than-light motion by choosing one preferred frame. Signals would then be required to move forward according to that frame's time, even if other observers describe them differently. No preferred frame has been confirmed. Tests of Lorentz symmetry have found no reliable sign that one state of steady motion is fundamentally special. Any new theory introducing an absolute background would need to explain why it remains so well hidden. Another proposal is self-consistency. Alice may receive a warning from the future, but physical events would somehow prevent her from acting in a way that removes the message's origin. Every part of the loop would fit with every other part. This avoids a direct logical contradiction, but it creates difficult questions. Where did the information first come from? What mechanism enforces consistency? How are probability and choice defined inside the loop? No experiment has shown such a system operating through faster-than-light communication. The anti-telephone is therefore not a proof that every unusual superluminal mathematical effect is impossible. It is a constraint. Any theory allowing genuine faster-than-light information must explain what happens to causality. It cannot simply add greater speed to ordinary communication and leave the rest of relativity untouched. This is the point where the original question changes character. At first, faster-than-light travel seemed like a problem of propulsion, perhaps a stronger engine, a more advanced fuel, or an unknown particle could shorten the journey. Now the deeper cost appears. The light speed limit protects more than distance. It protects the order that allows one event to produce another. Inside the light cone, observers may disagree about clocks, lengths, and simultaneity while still sharing one causal history. A message can be delayed. A journey can last different amounts of time. An answer cannot arrive before it's questioned. A controllable signal outside the cone threatens that common history. It can cross the region where temporal order depends on the observer, return through another frame, and close upon its own origin. The result is not merely a very fast warning. It is a warning whose existence may depend on preventing itself from being sent. That is why c is not merely the speed of light. It is the speed at which the order of physical influence remains safe. The anti-telephone shows what controllable, faster-than-light information could do. It does not tell us whether anything capable of carrying such information exists. That brings us to tachyons. A tachyon is a hypothetical entity defined not as an ordinary particle accelerated through c, but as something that would always move faster than light. It would belong entirely to the spacelike side of the boundary. The distinction is essential. A proton begins below c and remains below it regardless of how much finite energy an accelerator supplies. A photon exists on the light-like boundary. A traditional tachyon would begin beyond that boundary and remain there. None would cross naturally into another category. For ordinary matter, adding energy increases speed while keeping the object below c. The gain becomes progressively smaller as the boundary approaches. In simplified tachyon models, the relationship would be reversed. Adding energy would slow the tachyon towards c from above. Removing energy would allow it to move faster. At lower and lower energy, its speed could grow without limit. This already shows how misleading the word particle may become. A tachyon would not behave like a familiar object with an unusually powerful engine. Its relationship between energy, momentum, and speed would be fundamentally different. It could not possess an ordinary rest frame. A massive particle has a frame in which it is stationary. A photon has no rest frame because no inertial observer can move beside it at c. A tachyon would also lack a rest frame, but from the opposite side. If it were always superluminal, no ordinary observer could move quickly enough to become stationary relative to it. It would have no history of sitting still, accelerating, and departing. It would exist only as motion. When equations from special relativity are extended into the faster-than-light domain, terms associated with mass can involve imaginary numbers. Imaginary numbers are not meaningless or fictional. They are essential mathematical tools used throughout physics. But an imaginary mass does not mean that a tachyon would be made from supernatural matter. It means the familiar massive particle interpretation no longer works in the same way. The equations are warning us that we have entered another physical category. Mathematics can explore such a category. That does not prove nature occupies it. No confirmed experiment has detected a freely propagating tachyon carrying controllable information outside the light cone. No accelerator has produced a verified particle that crossed from time-like motion into a spacelike path. Claims of superluminal particles have appeared before. They usually emerge from difficult timing measurements, detector problems, incomplete models, or statistical fluctuations. One famous case occurred in 2011, when the OPERA experiment reported that neutrinos sent from CERN appeared to arrive at a detector beneath Gran Sasso in Italy, slightly earlier than light would have crossed the same distance. The result attracted intense attention. Neutrinos are real particles, and the experiment involved a carefully measured journey of more than 700 kilometers. A genuine superluminal result would have transformed fundamental physics. The collaboration investigated. Problems were found in the timing system, including a faulty fiber optic connection and another clock-related effect. After corrections and further measurements, the neutrino speeds agreed with relativity. The episode is valuable because it shows how science responds to an extraordinary signal. Researchers did not preserve the dramatic interpretation at all costs. They examined the equipment, published corrections, and allowed the evidence to remove the claim. Across hundreds of kilometers, a loose connection had briefly resembled a new law of nature. The word tachyon also appears in modern theoretical physics with another meaning. A field may be called tachyonic when a proposed state is unstable. In such cases, the mathematics does not necessarily predict particles racing through a laboratory faster than light. Imagine a ball balanced at the top of a smooth hill. The position can be described, but it is not stable. The slightest disturbance causes the ball to roll away toward a lower energy state. A tachyonic term in a field theory may play a similar role. It can indicate that the assumed vacuum is not the true stable configuration. The important physical process is then a transition to a different state, not the emission of superluminal messengers. This distinction matters because the presence of a negative mass-squared term in an equation is sometimes mistaken for evidence that a theory contains usable faster-than-light particles. Usually, it is evidence that the starting point is unstable. Even if a freely propagating tachyon were proposed, many questions would remain. How would it be produced? How would ordinary matter detect it? Could the source choose when to emit it? Could information be encoded in it? Would its propagation select a preferred frame? Would exchanges between moving observers create causal loops? A theory must explain more than whether a space-like momentum can be written mathematically. It must show how the entity participates in a stable, probabilistic, and causally consistent physical world. Relativistic quantum theory makes this especially demanding. Particles are excitations of fields. The theory must preserve meaningful probabilities, stable energy behavior, and consistent relationships between creation and absorption. Because observers may reverse the order of space-like separated endpoints, one frame's emission can become another frame's differently interpreted process. Mathematical reinterpretation can sometimes reorganize negative energy descriptions. It does not automatically remove the causal problem if controllable communication remains possible. The same cost returns. A real tachyonic messenger would require relativity to be modified, communication to be restricted, or unusual causal structures to be accepted. None is logically impossible merely because it feels unfamiliar. Physics has adopted many ideas that once seemed strange. The proper question is whether evidence requires them. At present appear that any danger of a nuclear war is. Particle accelerators show massive particles approaching C from below. Electromagnetic and gravitational signals respect the causal boundary. Precision experiments have found no reliable channel carrying chosen information outside a light cone. Tachyons remain valuable mainly as conceptual probes. They clarify the difference between crossing the limit and existing beyond it. They reveal how energy and momentum would have to behave in a space-like regime. They expose the connection between superluminal motion, stability, and causality. And they remind us of a quiet rule in theoretical physics. An equation can describe more possibilities than nature chooses to realize. The faster-than-light side is mathematically discussable. That does not make it physically inhabited. We can now leave hypothetical particles and turn toward effects that have genuinely been observed. Situations in which something seems to outrun light, while no matter or message crosses the forbidden boundary. The appearances are real. What moves within them is not always what the eye first names. The fastest-looking effect is not always the fastest-moving thing. Speed can be assigned to a particle, a pulse, a shadow, a wave crest, a pattern, or the point where two shapes intersect. Each may have a measurable velocity. Only some represent matter, energy, or new information traveling from one location to another. A laser beam gives us a simple example. Imagine a powerful laser aimed at a distant wall. Rotate the source slightly, and the illuminated spot sweeps across the surface. If the wall is sufficiently far away, a tiny change in angle creates an enormous displacement. The spot can move faster than light. No individual photon crosses the wall sideways. The photons reaching the first location travel directly from the source to that point. A different group travels toward the next location. Nothing moves along the wall from one illuminated patch to another. The spot is a sequence of separate arrivals. An observer at the first point cannot place a message on the moving spot and send it to the second point faster than light. The locations share a common cause at the laser, but they do not communicate with one another across the surface. A shadow behaves similarly. If a blocking object moves in front of a distant source, the edge of its shadow can sweep across an even more distant screen at a superluminal rate. Darkness is not a substance being transported. One point becoming dark does not send a physical influence sideways to darken the next point. Both changes result from the blocker's motion and from light traveling along separate paths. Relativity does not forbid the position of a pattern from changing faster than c when no causal influence travels between the pattern's successive locations. Wave motion makes the distinction more subtle. A wave may possess a phase velocity, a group velocity, and the signal front velocity. The phase velocity describes how a selected point in a repeating wave pattern moves under certain conditions. A crest or phase can advance faster than light, but an endlessly repeating wave contains no identifiable beginning. Every crest resembles the next. Observing another identical crest does not deliver a new decision made by a distant transmitter. A real message requires variation. The source must switch the wave on, alter its amplitude, shift its frequency, or arrange a sequence that the receiver can recognize. That variation is carried by a pulse or by a collection of frequencies. The pulse envelope often moves at the group velocity. In simple materials, this value tracks the transport of energy and information reasonably well. In strongly dispersive systems, however, the pulse can be distorted. Different frequencies are delayed, absorbed, or amplified by different amounts. The leading and trailing portions change shape. The maximum of the outgoing pulse may appear earlier than expected. A measured group velocity can then exceed c, or even take a negative mathematical value. The pulse has not travelled backward through time. The material has reshaped it. The peak emerging from the far side is not necessarily one intact feature that entered the material and raced through unchanged. It may be reconstructed from components already present in the pulse's leading edge. The genuinely important boundary is the arrival of unpredictable information. Imagine a transmitter that remains silent and then switches on at one chosen moment. Before that decision, no earlier pulse shape contains the message. The first physical change separating silence from signal is sometimes called the front. According to ordinary relativistic physics, that front does not propagate outside the local light cone. Quantum tunneling provides another apparent challenge. A quantum particle approaching a barrier does not behave like a tiny classical ball. Its wave function extends into the barrier and, under suitable conditions, beyond it. Measurements of tunneling time can produce values suggesting that the transmitted pulse crossed the barrier extraordinarily quickly. But the experiment does not show one intact particle entering the barrier, following a hidden classical route at a measured superluminal speed and emerging unchanged. Much of the incoming wave may be reflected. The transmitted portion is selected and reshaped. Different definitions of tunneling time describe different aspects of the process. The subject remains physically interesting because quantum motion does not always fit classical travel time intuition. Yet tunneling has not produced a reliable device that sends a chosen message outside the receiver's light cone. Astronomy offers another striking example. Jets launched from regions near black holes can appear to move across the sky faster than light. The material itself remains below. The illusion occurs when a jet travels almost toward Earth at a relativistic speed. During the time the material moves sideways across our view, it also moves closer to us. Light emitted later has a shorter distance to travel than light emitted earlier. The arrival interval becomes compressed. When astronomers divide the apparent change in position by the shortened interval between received images, the calculated transverse speed can exceed. Nothing locally travelled faster than light. Geometry and signal delay created the appearance. These effects are not measurement mistakes. A laser spot genuinely can sweep superluminally. A wave phase genuinely can exceed. A pulse peak genuinely can emerge earlier than a simple model predicts. A distant jet genuinely can display apparent superluminal motion. The mistake begins only when the speed of a feature is assumed to be the speed of a causal influence. Relativity protects information, not every imaginable pattern. The question to ask is always the same. What moved from the first location to the second? Was it matter? Was energy transported? Could a sender choose a new message? Could the receiver decode that choice before an ordinary light signal arrived? If the answer is no, the measured superluminal speed does not create the anti-telephone. It cannot return a reply into the sender's past. This distinction may seem technical, but it describes something physically simple. A pattern can have a position without possessing a body. A wave peak can have a speed without carrying the earliest new information. An image can move across a detector without one object crossing the distance. The universe allows these appearances because they do not rearrange causal history. What remains absent is the one ability needed to do that, making a freely chosen decision here available there before light could arrive. The patterns may outrun the limit. The message does not travel with them. A charged particle can move faster than light through water. The blue glow surrounding the core of a nuclear reactor is visible evidence. This light is Cherenkov radiation. It appears when an electrically charged particle moves through a transparent material faster than the phase velocity of light in that material. The particle may be an energetic electron produced by radioactive decay or by another high-energy process. It passes through water, disturbs the charged particles within the molecules, and leaves behind a coordinated electromagnetic wake. Nothing in the process exceeds the fundamental speed limit. The key lies in the phrase, through the material. The quantity c is the speed of light in a perfect vacuum. It is the invariant causal speed built into spacetime. Light propagates more slowly through water, glass, and many other transparent materials. This does not mean a photon becomes a tiny vehicle forcing its way through a crowded liquid. Light interacts with the material's electric charges. Those charges respond to the electromagnetic field, and their response contributes to the wave that continues forward. The combined interaction changes the effective propagation through the medium. In water, the phase velocity of visible light is roughly 3/4 of its vacuum value, with a small dependence on wavelength. An energetic electron moving at 9/10 of c remains slower than light in a vacuum. Yet it can move faster than the light wave propagating through the surrounding water. The situation resembles a supersonic aircraft. Sound waves spread through air at a finite speed. If an aircraft moves faster than those pressure disturbances, the waves cannot escape ahead of it. They accumulate into a shock front and produce a sonic boom. Cherenkov radiation is often described as an electromagnetic counterpart. A charged particle moving through matter polarizes nearby atoms and molecules. Their electric charges shift slightly in response to the particle's field. After the particle passes, those charges return toward their usual arrangement. At lower particle speeds, the emitted contributions do not combine into a strong, organized cone. They tend to cancel or spread without producing the characteristic glow. When the particle outruns the medium's light wave phase velocity, the geometry changes. Disturbances created at successive points overlap along a cone behind the particle. Along that cone, their phases reinforce one another. The result is coherent radiation. The angle of the cone depends on the particle's speed and the material's refractive index. By measuring that angle, physicists can infer how rapidly the charged particle was moving. This makes Cherenkov light more than a beautiful byproduct. It becomes a scientific instrument. Large detectors use enormous volumes of water or ice surrounded by sensitive light sensors when energetic particles pass through, or when other particles create fast, charged secondaries. The resulting flashes reveal direction and energy. Neutrino observatories rely on this principle. A neutrino carries no electric charge, so it does not directly produce Cherenkov radiation. But on rare occasions, it collides with matter and creates a charged particle. That secondary particle can move through the detector faster than light propagates through the water or ice. A cone of faint blue light spreads outward. By measuring which sensors detect the light and when they detect it, researchers reconstruct the direction of the original interaction. An almost invisible neutrino leaves a visible geometric signature. In nuclear reactors, energetic electrons move through the cooling water around the core. When their speed exceeds the local phase velocity of light, they create the familiar blue glow. The color does not mean the water is burning, or that the core has become hot enough to shine blue. Cherenkov radiation is produced across a range of wavelengths, with greater intensity generally toward the shorter visible wavelengths. Human vision perceives the combined glow as blue or blue-violet. The image is calm and precise. Particles too small to see pass through clear water. The material responds with a cone of light. The glow measures speed through geometry rather than through a dial. But the effect does not create a faster-than-light message. The charged particle remains below. An observer farther ahead cannot receive information from it before a light signal traveling through a vacuum along a comparable route could arrive. No signal escapes the vacuum light cone. This is why the phrase "speed of light" must be handled carefully. There is the invariant vacuum speed. There are also phase and group velocities of light inside matter. These depend on how the electromagnetic field interacts with the medium. Relativity protects the first limit. It does not say that no material object may ever move faster than the reduced phase velocity of light in water. A person can walk faster than light propagates through certain laboratory systems, engineered to produce extreme delays. That does not make the person relativistically superluminal. The comparison involves a wave slowed by material interactions. The same is true of Cherenkov particles. They are faster than light in the medium. They are not faster than the causal speed of spacetime. The particle also loses energy while producing the radiation. It cannot continue emitting indefinitely without an energy source. As it slows, it eventually falls below the Cherenkov threshold. The blue light stops. The sequence is complete. A charged particle enters the material with sufficient speed. Its field polarizes the medium. Successive disturbances reinforce along a cone. Radiation carries energy away. The particle slows until the condition is no longer satisfied. Every stage remains inside ordinary cause and effect. There is no crossing from a time-like path into a space-like one. No observer sees the particle outrun a vacuum light beam beside it. No reply returns before the original event. Cherenkov radiation is spectacular because it shows that a speed limit must always be tied to the quantity being measured. Sound possesses one speed in air and another in water. Light possesses an invariant speed in a vacuum, while its effective propagation through matter depends on the material. A particle may exceed the second without threatening the first. The blue glow is not a crack in relativity. It is relativity operating inside matter, and it prepares us for a subtler possibility. Perhaps nothing travels between two distant locations at all, yet the outcomes measured there still seem joined. Quantum entanglement appears to connect distant particles without waiting for light to cross the space between them. Two particles are prepared in one shared quantum state. They move apart. One travels toward Alice's laboratory, while the other reaches Ben. When the particles are measured, the outcomes display correlations stronger than any ordinary shared instruction seems able to explain. The distance may be meters. It may be kilometers. Nothing obvious crosses between the detectors at the moment of measurement. Yet, when the records are later compared, the results fit together with remarkable precision. Einstein found this deeply uncomfortable. With Boris Podolsky and Nathan Rosen, he argued that the quantum description might be incomplete. Perhaps the particles carried hidden information determining the outcomes in advance. John Bell later found a way to test broad versions of that idea. Bell inequalities define limits on correlations that can be produced by local, hidden variable models. Experiments can compare those limits with the predictions of quantum mechanics. Alice and Ben each receive one particle from an entangled pair. Each independently chooses between different measurement settings. Every measurement produces an outcome, which we may imagine as plus or minus. Alice cannot choose whether her detector displays plus or minus. She chooses how to measure. The individual result remains unpredictable. Ben sees the same kind of randomness. When each observer looks only at their local sequence, it resembles an unstructured series of outcomes. Neither can read the other's choices from it. Only later, after the records are brought together through an ordinary communication channel, does the entangled pattern appear. The correlation depends on which measurement settings were chosen. Across many trials, the outcomes violate Bell-type inequalities in the manner predicted by quantum mechanics. Nature does not behave as though every particle merely carries a complete local answer sheet from the source. That is the profound result. It is not a faster-than-light message. Alice cannot use her measurement to write a chosen symbol into Ben's detector. Suppose she wants to send one binary digit. She decides that one measurement setting will represent 0 and another will represent 1. Ben watches his outcomes. His local statistics remain random. Nothing in his laboratory reveals which setting Alice selected. Nothing tells him when she performed the measurement. He cannot distinguish her chosen 0 from her chosen 1 before additional information reaches him normally. Alice may alter the joint relationship visible when both data sets are compared. She does not alter Ben's local record in a controllable way. This is the central protection. Information requires more than correlation. A sender must be able to choose among distinguishable possibilities so that a receiver can recover that choice. Alice cannot control her individual outcome. If she receives plus when she hoped for minus, she cannot repeat the same measurement on the same particle and demand another answer. The original quantum state has already been changed by the interaction. She may measure another entangled pair. The next result is still unpredictable. Across many pairs, the correlations become unmistakable. No single local sequence becomes a message. Quantum teleportation follows the same limit. The name suggests that an object vanishes in one location and instantly reappears elsewhere. The real protocol transfers a quantum state using shared entanglement and ordinary classical information. Alice performs a joint measurement involving the state to be transferred and her half of an entangled pair. The measurement produces an ordinary result. She sends that result to Ben through a classical channel. Only after Ben receives it can he apply the correct operation and reconstruct the original state in his laboratory. Entanglement is essential. So is the slower-than-light message? Without Alice's classical information, Ben does not know which correction to perform. His local particle reveals nothing he can use to complete the transfer. Quantum teleportation therefore cannot outrun light. It also does not create a second, independent copy of the unknown state. Alice's original state is disturbed during the process, preserving the quantum rule against freely copying an arbitrary unknown state. Experiments testing Bell inequalities have become increasingly sophisticated. They have separated detectors, randomized measurement choices, improved efficiency, and closed major experimental loopholes. The work associated with these foundations was recognized by the 2022 Nobel Prize in Physics awarded to Alan Aspect, John Clauser, and Anton Zeilinger. The evidence confirms that quantum correlations cannot be explained by a broad class of local hidden variable theories. It does not provide an anti-telephone. Different interpretations of quantum mechanics describe the situation differently. Some speak of the wave function updating when a measurement occurs. Some treat the quantum state primarily as a tool for calculating probabilities. Some describe branching outcomes or relational states. These interpretations disagree about the deeper meaning of the formalism. They agree about the laboratory result relevant here. Ben cannot use his local data to determine Alice's distant choice before an ordinary signal arrives. This is the no-signaling principle. It allows quantum mechanics to contain non-classical correlations while preserving the operational causal boundary of relativity. The word operational matters. Quantum theory and relativity do not always fit together comfortably at the level of interpretation. A complete theory of quantum gravity remains unfinished. Questions about measurement, locality, and the nature of spacetime remain open. But the observed communication rule is clear. No entanglement experiment has allowed a sender to transmit chosen information outside a light cone. The universe permits a relationship stronger than ordinary shared preparation. It does not permit Alice to control the distant half of that relationship. When the records are finally brought together, the pattern appears to have extended across the separation. Neither record alone reveals it. The meaning exists in the comparison. That is why entanglement feels both immediate and unusable. It joins outcomes without carrying a sentence between them. It challenges the classical idea that distant systems must possess entirely separate descriptions. It does not give a traveler or transmitter a route into the past. The light-speed boundary survives in a subtler form. Quantum theory does not require every correlation to be built by a signal sent after the particles separate. It requires that no observer can control those correlations to communicate faster than light. The universe may be more deeply connected than classical intuition allows. Yet that connection remains quiet until ordinary information brings the distant records together. Entanglement preserves the light-speed boundary by refusing to carry a controllable message. The expanding universe preserves it in another way. Some galaxies are receding from us faster than light. This is not a laser spot, a reshaped pulse, or an illusion created by compressed arrival times. In the standard cosmological description, the distance between us and sufficiently remote galaxies can increase by more than 1 light-year during 1 year. Yet those galaxies are not locally violating relativity. The contradiction appears only when cosmic expansion is imagined as ordinary motion through a fixed space. That picture works for nearby objects. Earth moves around the Sun moves within the Milky Way. The Milky Way and Andromeda approach each other through their local gravitational environment. On the largest scales, however, galaxies are not simply flying outward through an unmoving emptiness. The geometry between distant unbound regions evolves with time. Imagine dots on the surface of an inflating balloon. As the balloon expands, each dot becomes farther from the others without crawling across the rubber. The surface between them changes. The analogy is limited. The universe is not known to be a two-dimensional surface expanding into an external room, and it has no confirmed central point outside space. But the image captures one useful idea. Growing separation does not require every galaxy to propel itself through local space. The farther apart two galaxies are, the more expanding space lies between them. Each small region contributes a little to the total increase in distance. Across a modest separation, the effect is small. Across billions of light-years, the combined recession rates can exceed. This relationship is associated with the Hubble expansion. Nearby galaxies generally show smaller recession rates. More distant galaxies generally show larger ones, once local gravitational motion is separated from the large-scale pattern. At a sufficient distance, the recession rate equals c. Farther away, it exceeds c. No observer standing beside one of those galaxies measures it racing past a nearby light beam. In its local region, light still moves at c. Matter follows time-like paths. Ordinary experiments obey the same relativistic laws. The superluminal value appears when we compare widely separated locations using a distance defined across an evolving spacetime. This distinction between local and global measurement is essential. Special relativity describes local regions where curvature and cosmic evolution can be neglected. General relativity describes curved and changing spacetime across large scales. In general relativity, the rate at which a large-scale distance changes is not constrained in the same way as the speed of an object passing a nearby observer. The causal speed limit applies locally. It does not require every possible distance between remote regions to increase more slowly than c. Picture a long chain of observers spread across the expanding universe. Each observer is close enough to the next that their mutual recession remains below light speed. No neighboring pair sees a local violation. Place many such intervals end to end. The distance between the observers at the two far ends may increase faster than light. The global value arises from many small local changes. No person in the chain watches a nearby object cross their local light cone. This also explains why a galaxy receding faster than light can still be visible. At first, that seems impossible. If the distance grows faster than light can cross it, how could a photon ever reach Earth? The answer is that the expansion rate has changed across cosmic history, and the photon's remaining distance does not stay fixed during its journey. A photon emitted long ago may initially have been carried farther from us in a global sense, even while moving locally in our direction at c. The expanding geometry increased the separation faster than the photon reduced it. Later, the balance changed. The photon entered regions where its local progress toward us overcame the growth of the remaining distance. It eventually arrived at a telescope. The photon never exceeded c. The galaxy never needed to slow from a local superluminal speed. The geometry changed while the light was traveling. This is why present recession speed does not alone determine visibility. The full expansion history matters. The light is also stretched during the journey. As the cosmic scale increases, the wavelength of traveling radiation grows. Light emitted in visible or ultraviolet wavelengths may arrive as infrared. This is cosmological redshift. For nearby galaxies, it resembles an ordinary Doppler shift. Across great distances, it reflects the changing geometry through which the light propagated. Astronomers use redshift, standard candles, the cosmic microwave background, and the distribution of galaxies to reconstruct the expansion history. In the late 1990s, teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees studied distant Type 1a supernovae. These stellar explosions appeared dimmer than expected in a universe whose expansion was merely slowing. The observations indicated that cosmic expansion is accelerating. The discovery did not identify the physical substance responsible. It revealed a large-scale behavior that the cosmological model must explain. The name dark energy is used for the component associated with this acceleration. Its underlying nature remains unknown. That uncertainty should remain separate from what is observed. We observe the redshifts and brightnesses of distant objects. We infer an expansion history that includes acceleration. We model the effect using dark energy or related descriptions. We do not yet know the complete physical identity of that component. The expanding universe therefore gives us a genuine faster-than-light quantity without a local superluminal traveller. What exceeds c is the rate of change of a large-scale separation. A spacecraft cannot freely use this as an engine. Nearby space does not carry the craft past a local beam of light. Bound systems such as atoms, people, planets, and galaxies do not simply expand with the cosmic scale. Local electromagnetic and gravitational forces hold them together. Expansion becomes important across the enormous spaces between distant, gravitationally unbound regions. So when cosmologists say that a galaxy recedes faster than light, they do not mean that a local speedometer aboard the galaxy displays a forbidden value. They mean that the distance defined between widely separated regions is increasing at a superluminal rate. Relativity remains intact because it never placed the same restriction on local motion and global geometry. Locally, light still marks the causal edge. Globally, the changing geometry can place regions across distances that light may struggle or eventually fail to overcome. That leads to a quieter consequence. Some galaxies are not merely receding faster than light now. Events occurring there may lie beyond the reach of every signal they could send us from this moment onward. A galaxy can be visible even while its present distance from us increases faster than light. The more difficult question is whether light emitted by that galaxy today will ever reach us. The answer is not always yes. Cosmic expansion can create horizons, boundaries separating events whose signals may eventually arrive from events that remain forever outside our causal future. A cosmic horizon is not a material wall. No spacecraft collides with it, no galaxy crosses a glowing line and disappears in one instant. The horizon is defined by the paths light can follow through an evolving universe. It asks whether enough future time and favourable geometry remain for a signal to complete its journey. We already live within one observational boundary. The universe has a finite age, and light travels at a finite speed. We can see only regions whose signals have had enough time to arrive since the early universe became transparent. This defines the observable universe. Its edge is not necessarily the edge of all existence. Beyond it may lie more galaxies, resembling what we can observe. Their light has simply not reached us. Another boundary concerns the future rather than the past. If accelerated expansion continues approximately as described by the standard cosmological model, there are events occurring now whose light will never reach Earth, no matter how long the future lasts. The space between us and those events will grow too rapidly for the signal to overcome. Locally, the light still moves at c. Every nearby observer along the route measures the photon travelling at the vacuum speed. Nothing slows it. Nothing violates relativity. Yet the total distance it must cross can increase faster than its local progress reduces that distance. The photon travels faithfully through each small region. The destination remains unreachable. This is a cosmological event horizon. It divides events that can ever influence us from those that cannot, given the future evolution of spacetime. The name resembles the event horizon of a black hole because both are causal boundaries. A black hole event horizon forms around a region where spacetime is curved so strongly that all future directed paths remain inward. A cosmological horizon arises because expansion separates distant regions too quickly for signals to cross. One is associated with collapse, the other with expansion. Neither is a material shell. These horizons also depend on the observer. A distant galaxy has its own observable region and its own future horizon. It may receive light from places we can never see. We may receive signals from places that never communicate with it. No location possesses a uniquely complete view. Each observer appears to stand at the center of an observable sphere because all received light converges upon that observer's present event. This produces a quiet symmetry. Every sufficiently distant observer inherits a different selection of ancient signals. Reality can be shared without being completely shareable. Cosmology contains several related boundaries that must not be confused. There is the present edge of our observable universe, limited by cosmic age and light travel time. There is the Hubble sphere, where a commonly defined recession rate equals c at a particular cosmic time. And there is the event horizon, determined by whether a signal emitted now or later can ever reach us. They are not the same. A galaxy can lie beyond the Hubble sphere and still send light that eventually reaches Earth. We already encountered that possibility. The expansion conditions can change during the photon's journey. The event horizon asks a stricter question. Not whether the galaxy currently recedes faster than light, but whether any future path remains for its newly emitted signal to arrive. The answer depends on the entire future expansion history. Observations support an accelerating universe. The simplest standard model describes dark energy as remaining approximately constant in density, while matter becomes increasingly diluted. If that behavior continues, gravitationally unbound galaxies will recede farther and faster. Their light will become increasingly redshifted. Photons will arrive with lower energy and at longer intervals. The galaxies will not suddenly vanish at one exact moment. They will fade. Visible light will shift into infrared and then into still longer wavelengths. Changes occurring there will appear increasingly slowed in the signals we receive. Eventually, practical detection becomes impossible. The galaxy may continue to exist. Stars may form, age, and die. Planets may orbit. A civilization there could build a transmitter and point it toward our region. But signals emitted after the relevant causal separation would never arrive. From its perspective, our future messages would also fail to reach it. The universe does not need to destroy two regions to make them permanently silent to one another. It only needs to increase the distance between them in the right way. This may be the most literal meaning of beyond light offered by known cosmology. There are events beyond the reach of any light that can ever come to us. They are not tachyons. They are not quantum messages hidden inside entanglement. They are ordinary physical events placed beyond future contact by the evolution of spacetime. Nothing about the local scene must look unusual. A star can shine normally beyond the horizon. A world can have weather, oceans, and nights. Yet no future telescope built here can reveal what happens there after causal separation becomes final. A larger mirror cannot collect photons that never arrive. A more sensitive detector cannot recover a signal that has no path into our future light cone. Technology can approach limits created by weakness, resolution, or noise. It cannot overcome the absence of causal contact. Closer to home, the picture is gentler. The Milky Way belongs to a gravitationally bound local group. Andromeda is approaching us rather than following the large-scale expansion away. Over immense time, the two galaxies will interact and merge. The local group is expected to remain bound while many distant galaxies fade beyond observation. Future observers could inherit a darker and apparently emptier sky. They might see more large merged galaxy and few obvious signs of the broader cosmos. The cosmic microwave background will be stretched to extremely long wavelengths. Distant galaxies revealing the expansion may no longer be detectable. Reconstructing the true history of the universe could become much harder than it is today. Our era is therefore unusual in a modest way. We can still observe the ancient background radiation. We can still map galaxies across vast distances. We can still see enough cosmic history to infer a universe extending far beyond our local home. The horizon has not yet erased that evidence. It has only begun the long separation. At the beginning of the journey, beyond light suggested speed, a machine accelerating past a number. Now it describes something quieter. A signal can travel at the full speed allowed by nature and still fail to arrive. Light does not lose a race against a faster object. It loses to the changing geometry of the remaining distance. The horizon marks no weakness in light. It marks the limit of connection. And once nature places regions beyond every ordinary signal, the temptation becomes understandable. Perhaps spacetime itself could be shortened so the traveller never has to cross the full distance. If a traveller cannot cross space faster than light, another possibility remains. Do not move faster through the distance. Change the path. General relativity describes gravity as the geometry of space-time. Matter and energy influence that geometry, while light and freely falling objects follow the paths it provides. Space-time curves around stars. It forms horizons around black holes. It expands across the universe. Perhaps, at least mathematically, it could be shaped into a shortcut. The best-known warp drive proposal was introduced by Miguel Alcubierre in 1994. In the idealized geometry, space contracts ahead of a spacecraft and expands behind it. The craft remains inside a region sometimes described as a warp bubble. Locally, the vehicle does not need to pass a nearby beam of light. It can remain nearly at rest inside its immediate environment. From far away, however, the bubble could carry it across a large distance in less time than light would require along the ordinary external route. The idea resembles cosmic expansion on a controlled, local scale. But writing down a geometry is not the same as creating it. Einstein's equations connect curvature with distributions of energy and momentum. Once a desired spacetime is proposed, physicists can calculate what kind of physical source would be required to support it. The original Alcubierre solution requires regions of negative energy density. Quantum field theory permits limited situations in which a local energy density can fall below a chosen vacuum reference. The Casimir effect is often mentioned as an example. But small and tightly constrained quantum effects do not show that an engineer can gather vast, stable amounts of negative energy and shape them into a moving shell around a spacecraft. The geometry would have to be created. It would have to remain stable. It would have to move in a chosen direction. And it would have to stop safely. Control becomes a problem because a superluminal bubble can form horizons. The crew may be causally separated from the leading edge of the structure. A command sent from inside cannot necessarily reach the region that must be changed to steer or stop the bubble. The vehicle could be carried by a geometry whose forward boundary lies outside its immediate control. The old causal difficulty also returns. A single warp route may look like a shortcut, but suitable combinations of superluminal journeys between observers in relative motion can create closed causal paths. The engine escapes the local speed limit only to encounter the same question waiting at the destination. Can the trip be arranged so that arrival precedes departure? A wormhole offers another version of the shortcut. Instead of moving a bubble across the intervening space, a wormhole would connect two distant regions through a shorter internal route. The familiar image is a folded sheet of paper. 2 points far apart on the surface are brought close together, and a passage joins them directly. The universe need not literally fold through an external room for the analogy to help. The essential idea is that the internal path through spacetime is shorter than the ordinary route outside. A traversable wormhole would have two openings, usually called mouths, connected by a throat. A traveller could enter one mouth and emerge from the other without crossing the full external distance. Locally, the traveller remains below sea. Globally, the arrival can occur sooner than a beam travelling through ordinary space. In 1988, Michael Morris and Kip Thorne studied conditions under which a wormhole might remain traversable. The difficulty was immediate. Ordinary matter tends to make the throat collapse. Keeping it open generally requires a distribution of stress and energy that violates familiar energy conditions. Again, the mathematical geometry demands a physical source, unlike ordinary matter. Even if a wormhole already existed, it would need to remain stable against collapse, radiation, and quantum effects. The tidal forces inside would need to remain gentle enough for a traveller or signal to survive. Its mouths would need to be placed where they were useful. And if the mouths experienced different motion or gravitational environments, their clocks could become offset. The shortcut could then connect not only distant places, but different external times. It could become another route toward a causal loop. Warp bubbles and wormholes are therefore not simply faster engines. They move the difficulty. The missing speed becomes unusual energy. The long distance becomes engineered geometry. The steering problem becomes a horizon problem. The early arrival becomes a causality problem. None of this proves that every shortcut is forbidden by a complete future theory. General relativity is classical. The most extreme geometries are likely to require a quantum description of spacetime that does not yet exist. A mature theory of quantum gravity may revise which structures are stable or physically meaningful, but an unknown theory cannot be used as evidence that the desired machine works. At present, no traversable macroscopic wormhole has been observed. No controllable warp bubble has been created. No known material can be assembled into the required geometry. These ideas remain valuable because they clarify what faster-than-light travel would really demand. It would not be enough to build a stronger engine. One would need to shape spacetime while preserving stability, control, and causal consistency. The spacecraft from the beginning still waits inside the light cone. A warp drive proposes moving the road beneath it. A wormhole proposes replacing the road with a doorway. Both approaches avoid local acceleration through. Neither removes the physical cost. The universe may allow more geometric freedom than ordinary space suggests. Its equations contain paths that resemble shortcuts. Yet every known shortcut returns us to the same boundary. What can be built? What can be controlled? What can remain stable? And can the traveller arrive without disturbing the order that made departure possible? The final answer does not depend on whether a line can be drawn beyond the light cone. Many such lines can be drawn. It depends on what nature allows those lines to carry, and whether cause and effect remain intact at the other end. We began with the spacecraft accelerating into the dark. Its engines continued to fire. The crew felt a steady pressure beneath their feet. The stars ahead shifted toward blue, and Earth watched the ship approach the speed of light through an ever-narrowing gap. There was no wall in front of it. There was no flash announcing the edge of ordinary physics. There was only a boundary the spacecraft could approach without crossing. We can now answer the question that followed us through the journey. What really happens beyond the speed of light? For an ordinary object with mass, nothing happens beyond it because known physics provides no continuous physical path carrying the object there. More energy increases momentum and brings the measured speed closer to No finite amount completes the crossing. The traveller remains inside the light cone. Light follows the cone's surface. It does not begin below the limit and accelerate upward. A photon in a vacuum is created moving at c, and no valid inertial observer can enter a frame in which it is stationary. Beyond the cone lies spacelike separation. It contains pairs of events too far apart and too close in time for light or any slower influence to connect them. Mathematics can describe a line joining those events. What nature has not shown us is an ordinary piece of matter or controllable message traveling along that line. This is the strongest answer supported by present evidence. The vacuum speed of light is not merely the highest number permitted on a speedometer. It separates different relationships between events. Inside the light cone, causes precede their effects for every observer. On the cone, light carries influence at the causal boundary. Outside it, distant events have no universal temporal order. One observer may say that event A occurred first. Another, moving relative to the first, may place event B first. That disagreement creates no contradiction, while the events remain causally disconnected. The danger appears when we imagine turning the separation into communication. A controllable faster-than-light message would allow some observers to describe its reception before its transmission, add a suitable return signal, and the reply can arrive before the original question was sent. That is why faster-than-light information threatens more than one accepted constant. It threatens the order that allows physical events to form a consistent history. No confirmed experiment has shown such a message. Massive particles have been accelerated extraordinarily close to C, but not beyond it. Electromagnetic and gravitational disturbances respect the same causal structure. Measurements once interpreted as superluminal particles have not survived careful testing. Several real effects still carry the language of faster-than-light motion. A laser spot can sweep across a distant surface faster than a shadow can cross a screen at a superluminal rate. A wave phase, or pulse maximum, can appear to advance unusually quickly. A relativistic jet can display apparent motion across the sky faster than light. None carries a freely chosen message between its successive locations, outside the light cone. The speed belongs to a pattern, a projection, a phase, or a reshaped feature. Cherenkov radiation gives us a visible form of the distinction. An energetic charged particle can outrun light as it propagates through water. The water responds with a blue electromagnetic wake. The particle is faster than light in the material. It remains slower than The glow does not reveal a broken causal boundary. It reveals that light's effective propagation through matter can be slower than its invariant speed in a vacuum. Quantum entanglement reaches deeper. Entangled particles display correlations that cannot be reduced to an ordinary local answer sheet prepared in advance. Bell tests have made that conclusion part of experimental physics. Yet each observer's local outcomes remain unpredictable. Alice cannot choose a result and make it appear in Ben's laboratory. The distant pattern becomes visible only after the records are compared through an ordinary channel. Entanglement connects statistics without transmitting a controllable sentence. It is more subtle than a hidden signal and less useful as a superluminal telegraph. Cosmology provides the clearest case in which a measured rate can genuinely exceed light speed without violating local relativity. The distance between sufficiently remote galaxies can increase faster than c because the geometry between them evolves. The galaxies do not locally pass nearby beams of light. What becomes superluminal is the change in a large-scale separation. Some events lie beyond our cosmological event horizon. Light emitted there today may never reach us, even while travelling locally at sea throughout its journey. Expansion can increase the remaining distance faster than the photon reduces it. This is not the same kind of speculation as a tachyon or a warp drive. Cosmic expansion and its present acceleration are inferred from multiple observations. What remains unresolved is the fundamental nature and future behavior of dark energy. We observe the expansion. We strongly infer its acceleration. We model the resulting horizons. We do not directly know the entire future history of the cosmos. Warp bubbles and wormholes occupy a more speculative category. General relativity permits geometries in which a traveller reaches a distant location sooner than light, following an ordinary external path. The traveller may remain locally below c because the path itself has been altered. But known versions introduce severe requirements: negative energy, instability, horizons, control problems, and possible routes to causal loops. There is no observational evidence that a traversable macroscopic wormhole or controllable superluminal warp bubble exists. So the phrase "beyond the speed of light" gathers several different ideas beneath one name. It can mean a space-like separation. It can mean a pattern moving faster than It can mean a charged particle outrunning light in matter. It can mean quantum correlations that carry no message. It can mean cosmic distances increasing superluminally. It can mean a theoretical shortcut through curved geometry. Only one meaning gives us the familiar dream of faster-than-light travel, an object or controllable signal locally crossing the vacuum light-speed boundary. That is the meaning nature has not shown us. The absence becomes less disappointing once we understand what the boundary protects. Because C is finite, the universe is not one instantly connected place. Every observation arrives from the past. Every conversation across space requires time. Every event is surrounded by a region it can influence, a region that can influence it, and a wider reality still beyond contact. The speed of light gives the universe sequence. It allows a cause to leave a trace before that trace becomes another cause. It prevents every distant event from collapsing into one universal present. A deeper theory may eventually revise part of this picture. General relativity and quantum theory remain incomplete when pushed together at the most extreme scales. New evidence could reveal structures not yet imagined. But any successful theory must recover the causal order measured so precisely in the world around us. It must explain why ordinary matter remains below, why usable information does not escape the light cone, why every tested local experiment continues to respect the same boundary, until evidence requires another answer. Beyond light is not a faster road waiting for a better engine. It is the name we give to separations ordinary influence cannot cross, appearances that carry no message, cosmic regions geometry has placed beyond reach, and mathematical shortcuts whose physical cost remains unknown. The spacecraft from the beginning is still accelerating. Its crew feels no wall. Earth sees its speed move closer to the limit, digit by digit, while the travelers' clocks and distances arrange the journey differently around them. The gap becomes smaller. It never disappears. Ahead of the spacecraft, light continues through the darkness at the same familiar speed, not racing to defend a rule, simply tracing, as it always has, the quiet boundary between what can touch the next moment and what must remain beyond it.